Welcome to another podcast. In this episode, we're going to be taking a look at the average value of a function. Now, this is one of those topics that typically students understand really well because they're able to basically compare it to something that they understand, which is how to take the average values of numbers. And so what I want to do is show you, if you have a data set, we all know how to take the average of that. I want to show you how that relates to the average value integral that allows us to find the average value of a function. So let's say, for example, that you collected data and you were looking at the weights of 5 people, and the data set that you ended up with was, I'll just call it the set X, containing the points or the observations 155, 143, 180, 105, and 123. Then I think we all know that the way you would calculate the average is to add up all of the points and divide by the total number of observations, which is 5. In this case, if you were to calculate it, it would be 141.2 pounds. So that's a fairly standard thing. Most of you learned that early on in your schooling. How does this relate to calculus? Well, if you let the function y equal f of x be continuous, meaning there's no breaks in the function, I want it to be continuous on the interval from a to b. Then what I want to do is look at a partition. So in other words, I'm going to take the interval from a to b, and I'm going to break it up into several pieces. This first piece, I'm going to call this the point x naught. The last piece is xn, and I'm going to break it up or partition it into x1, x2, and so on, all the way up to xn minus 1, so that there are n equal sized subintervals. And we're familiar with this concept of partitioning from looking at Simpson's rule, trapezoid rule, etc. We know, for example, that the width of each subinterval would be b minus a over n in this case. And here's what I want to do. I want to sample the interval. And here's what I mean by sampling the interval. I mean, I want to choose at random a point from each subinterval. So let's say that my sampling yields the following values. I get, for example, in here, I get x, I'll call it x1 bar. Sample in here, I get an x2 bar. Sample over here, I get an x n minus 1 bar. All totaled, they're n total samples because there's n total subintervals. Now, I want to take those x values and calculate the function's value at those points, yielding this sample of the value of f on the first interval, the value of f on the second subinterval, all the way up to the value of f on the last subinterval. Now, the idea is we take and we average those values, and if we have small enough intervals and enough points that we take a sample of, then we're basically recreating the function, and we take the average the exact same way that we would take the average of any value of numbers, because these are in fact numbers. The function valued x1 is a number, the function valued x2 is a number, so we're looking at a set containing a bunch of numbers, and we then take its average. What I'm trying to say is, if I wanted the average value of f based on this sample, it's easy enough to convince you, I think, that it's simply just this. Now, I'm going to divide the total by n because there's n total points, and then I'm going to make some adjustments to this. For example, I can write this as follows: 1 over n times, if you look at the numerator here, this is simply just a sum of the first n sample points, f at x bar sub k. So this is our summation notation for that. And then because delta x is b minus a, then that says that delta x over b minus a is the same as 1 over n. So I'm going to replace 1 over n with delta x over b minus a. And now it's starting to look like something we recognize. If I then take and put the delta x inside the sum, which I can do because it doesn't involve k, because each one of these is a consistent subinterval width, then as n goes to infinity, this is a Riemann sum. And the Riemann sum's limit is an integral. In this case, the integral is the integral over the entire interval, which is the interval from a to b. F at the sample point in the limit becomes f at every point, not just in certain subintervals, but every point on the interval from a to b. And delta x becomes the differential dx. And so the point here is, if I want to talk about the average value of a function, the average value of the function f of x, we typically put a bar like this over things we're taking the average of. So if I say bar f of x, that is the average of the function f. And in this case, this is its formula. So this is really no different than how you would calculate averages for anything else. It's just we're using the power of calculus and the idea of taking smaller and smaller subintervals to create a formula that's really nice to look at, really nice to use. We've got the 1 over b minus a integral a to b of f of x dx. And in the videos that are coming up, we're actually going to look at why this is extremely important and how we can use it. But for now, I just want to make sure that you know where this formula comes from. All right, thank you for watching.